All right, let's dive right into this explainer. We all know that wild feeling of typing a prompt and getting a seamlessly composed essay back in literal seconds. But today, we're going to peel back that conversational interface. We are looking strictly at the architecture, the math, and the absolutely staggering scale that actually drives large language models.
So, as a quick refresher, think of the core mechanism kind of like finding a movie script, where the AI's dialogue is just torn off. You feed the intact part into a machine, and that machine predicts the single most likely next word. You write that down, feed the slightly longer script back in, and loop it over and over until the scene is completely finished. That sequential prediction, word by word, is the heartbeat of the system unfolding behind your screen.
So what this means is, at its core, a large language model isn't actually thinking. Not in the human sense, anyway. It's really just a highly sophisticated mathematical function. Its entire job is to assign a probability to every possible next word for any given piece of text. But, here's a really fascinating quirk. If the model always just picked the single highest probability word every single time, the output would feel super robotic and repetitive. So to make it feel natural, the system occasionally selects less likely words entirely at random. The model itself is deterministic, it's doing the exact same math every time, but because of that slight randomness injected into the selection, you get a completely unique answer each time you give it the same prompt. Pretty cool, right?
Okay, part 1. Tuning the billions of dials. To make these predictions, the models use what we call parameters. Think of them literally as hundreds of billions of continuous numerical dials. Now, when a model is first created, nobody is manually setting these. They start completely at random, which means those first outputs are just absolute gibberish. But as massive amounts of text examples are fed in, the model guesses the next word, compares its guess to the actual word, and then this algorithm called backpropagation steps in. It calculates the difference between the guess and the correct word, and mathematically tweaks those billions of dials just a tiny, tiny fraction. And over trillions of examples, the model slowly learns to make incredibly accurate predictions.
Moving on to part 2. The mind-boggling scale. To really wrap your head around the sheer scale required to tune all those dials using text pulled from the internet, let's try a little thought experiment. Imagine you, yes you, had the superpower to perform 1 billion mathematical additions and multiplications every single second, non-stop. If you had that power, how long do you think it would take you to do all the math required to train just one of the largest language models? A year? Maybe 10,000 years?
Well, the answer is truly mind-boggling. Even doing a billion operations a second, it would take you well over 100 million years to complete the math for a single massive model. No way, right?
And the data itself is just as vast. To put that into perspective, just to read the sheer volume of text used to train a slightly older model like GPT-3, a human reading nonstop, 24 hours a day, 7 days a week, would need over 2,600 years to get through it all. And remember, the newer models train on significantly more data than that.
Which brings us to part 3, becoming a helpful assistant.
So that staggering computational process we just talked about, that is only the pre-training phase. It's literally just absorbing the internet to autocomplete text. But autocomplete doesn't equal helpfulness. If you ask a pre-trained model a question, it might just generate another similar question instead of answering it, purely because, well, that's what happens on internet forums. So, to become what we use today, these chatbots go through a second, entirely different phase called reinforcement learning with human feedback, or RLHF. This is where human workers actually interact with the model, flagging unhelpful or incorrect predictions. Those corrections further tweak the parameters, essentially teaching the model to prioritize giving the kind of helpful, safe answers that we actually want.
All right, part 4. The transformer breakthrough. Now, to handle all this staggering data, the industry relies heavily on GPUs, specialized computer chips optimized for running tons of operations at once. But hardware alone wasn't enough to get us here. Before a massive algorithmic breakthrough in 2017, most models processed text sequentially. They had to read one word at a time, start to finish, which created a huge bottleneck. Then, a team at Google introduced the transformer architecture. This was a real game changer. Instead of reading sequentially, transformers basically soak in all the text simultaneously, processing it entirely in parallel. It completely revolutionized the speed and scale of AI training.
So, let's actually break down how this parallel processing works under the hood. First, since mathematical models can obviously only handle numbers, every single word gets encoded into a long list of numbers. Second, the model applies a special operation called attention, which refines the context. Third, It all passes through a feed-forward neural network, which gives the model extra capacity to store complex language patterns. And finally, after cycling through those steps many times, it spits out that final prediction probability for the next word.
But the real magic here lies in that attention step. Think of it as giving all these separate lists of numbers a chance to look around and instantly talk to each other. They refine their meanings based entirely on the surrounding context. Take the word bank, for example. By itself, the numbers encoding it are totally ambiguous. But if the surrounding words relate to water and nature, the numbers for bank mathematically shift to encode the much more specific concept of a riverbank. And all of this highly complex contextual shifting is happening simultaneously, in parallel.
And finally, part 5, the magic of emergence. After flowing through billions of parameters, attention operations, and neural networks, the final output we get is uncannily fluent. But here is the ultimate paradox. Even though human researchers design the exact framework, the specific behavior of the model is an emergent phenomenon. It's just the unpredictable result of how those hundreds of billions of dials settled after trillions of tweaks. Because of this, it's actually incredibly challenging for even the brilliant engineers who built it to look inside the model and pinpoint exactly why it chose a specific word. It's wild.
Which brings us to the absolute most exciting, and honestly, kind of daunting part of this entire field. As we've seen, these models are really just sophisticated math functions, tweaking dials to predict the next word. Yet out of these simple probabilities, genuine fluency and reasoning-like behavior have magically emerged. It leaves us marveling at the math, right? And it makes you wonder, as we keep pushing the boundaries of scale, computing power, and data, as we tune the next trillion dials, what astonishing new emergent capabilities are we going to see next?